Bismillahirrahmanirrahim. Assalamu alaikum, dear students. Welcome to the next class of CS131 discrete structures. We are talking about chapter 10 graph theory, and in this before this particular lecture we have already discussed a few topics related to graph theory, which basically include the basic introduction and terminology of graph theory in the first two sections, where we described what graph is, what are the different graph terminologies and special types of graphs that exist, directed and undirected, and as well as other types. We then discussed how is a graph represented in terms of in terms of its adjacency list and adjacency matrices, as well as incidence matrices. And we discussed or applied the particular representation in terms of graph isomorphism, a very important topic where two graphs are basically, they can be morphed into the other into each other. So that was the topic of graph isomorphism. Then we discussed the topic about connectivity. How do we measure if a graph is strongly connected, weakly connected, or so on and so forth. So those kind of topics were discussed in section 10.4 under the topic of connectivity. And we finally discussed the topic of Hamilton paths, Hamilton circuits, Euler paths, and Euler circuits, and their various applications in different fields in our previous lecture. So in this lecture, we'll be talking about another application on the same line. So now that the basics are very clear to you, the basic terminologies and the graph theory concepts are absolutely clear to you, I'll now start talking about a concept which we call the shortest path problems. So let's share the screen and let's see the shortest path problems for this particular lecture. And I'm going to go into the full mode. Okay. So what are the shortest path problems? Well, many problems, they can be modeled using graphs with weights assigned to their edges. So once you assign weights to the edges, we get graphs that are weighted graphs. And as an illustration, let's consider how an airline system can be modeled. And I'll use a pen here. Okay, so for example, if we talk about mileage alone, right? So from San Francisco to New York, it takes us 2,534 miles to travel directly. So the flight that goes directly from in a particular airline from San Francisco to New York will travel 2,534 miles. On the other hand, a flight from San Francisco to Los Angeles, for example, takes 349 miles. If you break it up into two small trips, for example, from San Francisco to New York, you can go from San Francisco to Chicago in approximately 1,855 miles. And then you need to travel 722 miles further before you reach New York, from Chicago to New York. So this is how a graph has been divided. And you can see that each edge now has got a weight, which is basically the mileage that you need to travel from one point to another. And since this is an undirected graph, so this basically means that if you're going from San Francisco to New York or from New York to San Francisco, the distance traveled is the same. It's 2,534 miles. However, another way, one way of looking at this graph is through the mileage. Another way is the flight time, the time it takes to travel from one point to another. For example, from San Francisco, it will take us 4 hours and 5 minutes to reach New York directly. On the other hand, if you go through Chicago and then to New York, then it's going to take you 2 hours and 55 minutes on this side and 1 hour and 50 minutes from Chicago to New York. So this now we have changed the weight, but or the category, but effectively the graph remains somewhat similar, right? So it's the vertices are the same. It's just that the weights have changed. If you take a different feature or a different thing from which you need to identify. From mileage, now it is flight times, and that's the difference. Another thing, of course, is the fares, the price that it takes. So for example, from San Francisco directly to New York, it's going to cost you $129. However, if you now go from Chicago, it's going to cost you $99 plus $59, right? So again, this is another way of looking at the same graph with a different factor or feature that we are trying to explore. So this gives us the concept of what is a weighted graph. A weighted graph is a graph that have a number assigned to each edge. So you have a weight or a number that is assigned to each edge of a graph. In that case, the graph is called a weighted graph. Weighted graphs are used to model computer networks, communication costs such as the monthly cost of leasing a telephone line, the response times of the computer over these lines, or the distance between computers can all be studied using weighted graphs. So again, weighted graphs is a very important concept, and it can all be studied using basically different things. So for example, in this case, from San Francisco to Chicago to New York, this is the distance graph, the distance, for example. However, if you take the response time in a communication network, it takes us 5 seconds to respond if you want to get a response from San Francisco into Chicago, right? And so on. So this is the response time it takes between different vertices. And notice that the response time etc. is on the each edge and not on the vertex itself. So for example, from San Francisco to Chicago, it's 5 seconds. From San Francisco to Denver, it is 4 seconds. And San Francisco to Los Angeles, it's 3 seconds, and so on, right? So the weight is always on the edge and not on the vertex. And similarly, another thing is the lease rate per month, for example. And again, the lease rate of the line is different for different lines. And again, we see the cost. So again, this is a different weight that has been put on top of the on the same graph, right? The underlying graph is the same, but the edge weights have changed. And this is what we call weighted graphs. And as the weighted graphs are of course different in each graph. So let's talk about some problems that involve weighted graphs. For example, the first problem is that of least length. So if you want to determine a path of least length between two vertices, we'll be using weighted graphs. So let the length of a path in a weighted graph be the sum of the weights of the edges of this path. So if you take up a path and you sum up all the weights that are present in this path, that gives us the length of a path. So note that this use of the term length is different from the use of length to denote the number of edges in a path in a graph without weights. So if it is a graph without weights, we use the length to determine the number of edges that are present, right, in the path. However, now in a weighted graph, the length means sum of all the weights that are present in each edge in this particular path. So the question now is, what is the shortest path? That is the path of least length between two given vertices. So from point 1 to point 2, what is, for example, in this particular graph, what is the shortest distance between San Francisco and Boston, shortest traveling time or least cost, etc., and so on, right? So depending on the weight, whatever it is, we can change the question. And we basically want to travel from San Francisco to Boston. And there are multiple paths that are available. For example, you can either go on this path or take a visit from New York, ultimately Chicago, New York, and onwards. You can go from Denver, Chicago, New York, and so on and so on. There are a lot of different paths that are available for each question that is being asked. So the problem here is that we want to determine a circuit of shortest total length that visits every vertex of a complete graph exactly once. This problem is what we call the traveling salesperson problem. You want to visit each and every vertex of a complete graph exactly once and come back to the same path. And in this particular scenario, we want to have the shortest total length as well. So this is what we call the traveling salesperson problem, which asks for an order in which a salesperson should visit each of the cities on his route exactly once, so that he travels the minimum total distance. In this case, we want to minimize the total distance that is traveled, and that is done through using the traveling salesperson problem. And we want to visit every node exactly once in a way that we have minimized the total distance. Okay. So what is the length of a shortest path between A and Z in the weighted graph? So let this be a weighted graph, and we want to find the shortest path between A and Z, right, in this graph. So one way or a very simple way is to enumerate all the paths. So for example, go from A, B, C, Z, A, B, E, Z, A, so A, D, E, Z, A, D, E, B, C, Z, right? So in this way, we have actually enumerated all the paths. For each path, find the total weight or the length, right? And based on that, determine the one, select the path which has the shortest weight. This works very fine actually for really small examples like this one. However, with really complex graphs, as we'll see later, such an approach is infeasible. It's because it's what we call exploring exhaustive approach, and exhaustive approaches usually do not work when you have got a very large number of permutations or combinations. And in this case, of course, you had very few permutations or combinations, so this worked fine. However, for determining this for a large graph, we need a proper algorithm, and we'll see one such algorithm soon. So solve this problem by finding the length of a shortest path from A to successive vertices until Z is reached. So from A to successive vertices, you select the shortest path, and based on that, you can basically ultimately uh, reach Z, right? So that is the simplest algorithm. So start at A, add a shortest path vertex, maintain path lengths, and continue adding vertices until vertex Z is added. So keep on adding vertices. So in the first case, A to D, right, the vertex length is 2. Then the next vertex length, the shortest vertex length, you know to A to D now. The next thing is A to B with the shortest vertex length 4, right? Then the next is basically from A to E, which is 2 plus 3, 5 now. So A to E is 5. Then the next shortest vertex length is basically from B to C, right? So if you add that, so now you've got A to C is basically 7. So 7 from A to C, 5 from A to E. And then you have got basically the next is add 1 to reach Z. So A to Z is 6. And this is basically the path now is, because you have used this path, the path is AD, AE, and EZ. So AD, DE, and EZ are the 3 vertices that you need to use. This is the shortest possible path from A to Z. So note that the shortest path from A to Z could have been found by a brute force approach as well, like I said earlier on, by examining the length of every path from A to Z. So that's the thing that I told you was the simplest one. But however, this brute force approach is impractical for humans and even for computers for graphs with a large number of edges. That's the exact reason why I rejected that brute force approach. Another algorithm that we will probably need is what we call the Dijkstra's algorithm. And in Dijkstra's algorithm, the idea is simple. We proceed by finding the length of a shortest path from A to a first vertex, then the length of the shortest path from A to a second vertex, and so on until the length of the shortest path from A to Z is found. So from A to each other vertex, we'll try to find the first shortest vertex, second shortest vertex, and so on until finally there comes a point where we ultimately reach the point Z, right? So automatically, when you're finding the shortest paths, this algorithm can easily be extended to find the length of the shortest path from A to all other vertices of the graph, and not just to Z alone. Automatically, so whatever is being visited for finding Z, we'll probably reach there through the shortest path. We'll know that. And yeah, so all vertices that are being explored when we are exploring Dijkstra's algorithm, we'll automatically find the shortest path for them and not just Z alone. So what are the different properties of Dijkstra's algorithm? Well, the algorithm relies on a series of iterations. It's a multi-process method. A distinguished set of vertices is constructed by adding one vertex at each iteration. So in each iteration, you're actually adding just one vertex at a time. And then there's a labeling procedure that is carried out at each iteration. In this particular labeling procedure, a vertex W is labeled with the length of the shortest path. So for each vertex W, we have the length of the shortest path from A to W that contains only vertices already in the distinguished set. So those vertices that are already in the distinguished sets will be used to reach the new vertex W. The vertex added to the distinguished set is one with a minimal label among those vertices not already in the set. So the next vertex that will be added will always be the one that is that has the minimum label, and it is always taken from a set of vertices that is not already in the set, in the visited set. So it begins by labeling A with 0. So initially you give the starting vertex, the initial vertex, the value 0. So the labeled is A. And the other vertices will all be given the label infinity. Infinity is basically the label for every other vertex because that's the maximum possible value. Then for that, let us use the notation L not A is equal to 0. And the label of A is basically, which is our initial iteration. Zeroth iteration is 0, and the label of vertex V in iteration 0 is basically infinity for these labels before any iterations have taken place. So at iteration 0, the subscript 0 indicates for 0th iteration, and we give them these values. Everything else is infinity. Just the starting label is basically 0. These labels are then the length of the shortest paths from A to the vertices. These labels are basically the length of the shortest paths from A to the vertices, where the paths contain only the vertex A. So initially, of course, the only vertex that is contained is A. We start with that. Because no path from A to a vertex different from A exists, infinity is then the length of the shortest path between A and this vertex and every other remaining vertex. So Dijkstra's algorithm then proceeds by forming a distinguished set of vertices. It will take one vertex at a time. So let Sk be denoting this set after k iterations of the labeling procedure. So if you have labeled them, let the name be Sk, and it denotes the labeling procedure. We begin with S0 is equal to an empty set. So S0 is initially an empty set. The set Sk is formed from Sk minus 1 by adding a vertex u not in Sk minus 1 with the smallest label. So then you add a new vertex with the smallest label into the same existing set. Once u is added to Sk, we update the labels of all vertices not in Sk. So every vertex in Sk that is not present in Sk is also labeled and is updated so that LKV, so LKV label of vertex v at the kth iteration, right? So the label of vertex v at the kth stage is the length of a shortest path from A to V that contains vertices only in Sk, that is vertices that are already in the distinguished set together with U, right? So the new vertex would be added in here. So note that the way we choose the vertex U to add to Sk at each step to all optimal choice at each step, making this a greedy algorithm. And this is a greedy algorithm because it takes the shortest one and it moves on and on. And we'll see what a greedy algorithm is probably in a couple more courses, maybe when you study design and analysis of algorithms, or when you study the artificial intelligence course, you'll get to know this term very well. Or maybe even in data structures course as well, since that contains a bit of algorithms. So let V be a vertex not in Sk. To update the label of V, note that label of vertex V and kth iteration is the length of a shortest path from A to V containing only vertices in Sk. Of course, if there is some other path, if that is included, we are guaranteed that the shortest path, once you add the new vertex, will automatically come in after that. So this is at the moment, whatever vertices we have already put in the distinguished set, they are the only ones that are being used to determine the shortest path for any other vertex. However, if the shortest path exists through another vertex, once that vertex will be added, the shortest path will automatically be updated. So the update can then be carried out efficiently when this observation is used, that a shortest path from A to V containing only elements of Sk is either a shortest path from A to V that contains only elements of Sk minus 1, that is the previous distinguished vertices not including U, or it is the shortest path from A to U at the k minus first stage with the edge UV added. So k minus first stage, up till that point it is true. It may change later on, but up till the k minus first stage, we are sure that this is the shortest path. That's the first thing, right? Or it is actually the shortest path anyway. In other words, labeling of vertex A starting at A and reaching V, right? In the kth iteration is basically the minimum of labeling of the k minus first step, the previous step, right? For A to V, and LK minus 1, and you add to it the distance or the labeling of k minus 1 and AU plus the weight of the edge U and V. So you see, this is basically for V. This is for U. From U to V, we are trying to reach now. And this is basically just add the weight WUV weight into this particular AU to get the new value this. And whatever is the new value, if whatever is the minimum of the two new values, will then be the LKAV, where the weight of UV is the length of the edge with U and V as its endpoints. We'll see that in an example how we are going to apply this. So this procedure is iterated by successively adding vertices to the distinguished set until Z is added. So keep on adding one vertex at a time until finally the vertex Z is added. When Z is added to the distinguished set, its label is the length of our shortest path from A to Z. So once you add the vertex Z, then until that particular stage, until the kth stage, it is its label is going to represent the length of the shortest path from A to Z within up to stage K, right? And we'll see how that works. So here is how we need to apply the Dijkstra's algorithm. In Dijkstra's algorithm, the weight is basically the connected simple graph. The input is basically a graph G with weighted connected simple graph with all weights positive, right? So in case of negative weights, it is not going to work for sure. However, for the positive weights, it works absolutely fine. And let's suppose that G has vertices A, which is V0, V1 till Vn. And the final vertex is basically Z, and lengths W, Vi, Vj, where W, Vi, Vj is basically infinity. If there does not exist an edge between Vi and Vj. So it's basically a matrix of lengths is given, and it's infinity for the ones where edges do not exist, and it's the weight or the actual edge length for edges that are given. So like we said initially, for each vertex in there, we need to label it with infinity, started with infinity. Then the initial vertex is labeled 0, and we start with an empty path. So now the labels are initialized so that the label of A is 0 and all other labels are infinity, and S is basically an empty set at the start. So while Z is not does not belong to S until we don't get a Z, what we do is U is equal to A. U is basically a vertex not in S with LU minimal. So with the minimal label, we select a vertex U. Then we actually put it, we get a union of S and U and put this in S. And then for all vertices V not in S, all vertices that are not in S. So for example, in this case, we'll start with the vertex A, right? And put that A, that is a vertex that is not in S, S was empty. And LU is minimal, that is A. So we put A at the start in the first step. And later on, this while loop is going to keep on adding more and more vertices. For all vertices V not in S, so all vertices V that are not in S, we basically actually we add if LU label of U plus WUV is less than LV, right? So it's if it's less than infinity, or if there's a value given and this new value is still less than LV, then in that case LV will be updated to LU plus WUV. This adds a vertex to S with minimal label and updates the label of vertices not in S. And finally, it should return the labeling of Z, where LZ is equal to the length of a shortest path from A to Z. And we'll see how this works in a bit of an example here. So let us suppose that we have this graph, right? So we want to find the minimal distance from A to Z. We want to reach from this point to this point. So we initialize it. And this is how I want you to give me the answer as well. So you draw the graph again, like you label it right away. This one is labeled A. The label A has distance 0, while every other is labeled infinity. Note that this is a weighted graph, right? So each edge has a weight corresponding to it. So now everything else is infinity. Then we start with the minimal one. Now the set contains A. You can insert A there. And we know that the shortest label from this point, there are two possible candidates. You can reach B through A by using distance 4. You can reach to C through A using a distance of 2. So through A means that A, so now you've got 4A here and 2A. In the next step, we note that from C, which is the next shortest one, we can actually reach B by traversing 3 lengths. So now, since this 3 is smaller than 4, hence this 4 is going to be replaced by 3AC. However, the other things that we can reach from this point is by using C is basically D by using 2 and then 8, so 10 AC. Similarly, from C you can reach E by using this 10 again, so 12 for AC as well, right? So you can actually reach E from A by using 12 distance by using AC. On the other hand, 10 AC by using, again, you can visit D using this. So of course, the next thing is when you visited C, the next thing is you would want to visit B now. And once you visit B, we notice that some things will be updated. For example, this one for D, since this has a link to D, right? And a link to C and a link to this. The link to C is not possible because A, C, B, C, right, is this kind of a repetition. So that's not possible. So this will not be updated. A will not be updated as well because, and that is where you need to know that there is no negative distance. If there's a negative distance, this one, this loop will be always using the negative distance to feed in the distance. And that is not possible really. In an algorithm, it will not work at all. And that is why you don't need a negative distance. But the idea here is simple. So B to D is a possible chance. So 3 plus 5 is 8. And hence 8 is less than 10. So we'll update this one, right? But you'll notice that everything else is kind of the same. So now A, C, and B have been used. Let's reach the next smallest label, and that is D now, right? So now let's try with D. And with D, it's basically that you can reach Z by using 14. So A, C, B, and Z is A, C, B, and finally D, A, C, B, D, and you can reach Z, right? So for that, the cost is 14. And if you take it from 8 to E, so from D to E, it takes 8 plus 2, 10. 10 is less than 12, right? So this is going to be updated and it now becomes A, C, B, D, right? So that's the path that you need to reach E. And these two are updated. So next, the lowest path is basically E, right? So you select E, and with E, the only thing that you can update is possibly Z. And if you update Z by taking this 3, we notice that now the distance is 13 A, C, B, D, E. The only edge that is only node that is left is Z. And once you take the next Z, we know that the path in the next step is going to be basically A, C, B, D, E, and Z. So that's the path that has the shortest distance or shortest weight. And the weight or the traverse that you need to, the amount of distance that you need to traverse from A to Z is 13 units. And that is your final answer. So once we have got this out, that is the time when you need to stop. You need to notice one thing, that why don't we stop once we already know that Z is equal to 14? For example, once we get for Z, why don't we stop here? The reason is that the algorithm only guarantees that whenever a particular node is being taken out, only at that time will we be sure that it is the shortest distance possible from the starting node to this point, only at that time. But before that, until a node is not taken out, like at each step, each of these is taken out, we will not be able to identify, it might be updated. Like in this case, it did get updated, although you assigned 14, but it did go down to 13 in the next step. And it was, once it was taken out, only at this point are we sure that the distance is 13 and ACBDE, not at the previous step. So let's talk about some of the theorems. The Dijkstra's algorithm finds the length of a shortest path between two vertices in a connected, simple, undirected weighted graph. So Dijkstra's algorithm is guaranteed to find the length of the shortest path between two vertices in a connected, simple, undirected weighted graph. Then the Dijkstra's algorithm uses a complexity of, let's say it uses n square operations, different operations, addition and comparisons, to find the length of a shortest path between two vertices in a connected, simple, undirected weighted graph with n vertices. I'll not discuss it for now, but we'll all understand it better once we discuss the complexity. So this is basically a polynomial time algorithm and not an exponential algorithm, which is good, and which is why it can be used to find the minimal shortest paths, the lengths of them. So that brings an end to this particular chapter. I think the important thing here is what you need to know how to do it. So given a graph, you should be able to find, you should be able to apply the Dijkstra's algorithm. You should basically redraw the graph 10 times again. And with each time you're updating the labels. That's one way. Another way is that you're basically, you draw the graph only once, but put out all the vertices and their labels into separate vertices, their labels and their paths in a separate column. And also you also indicate which vertices have been used by basically circling them for each step. So in the first step, you have got vertex labels, paths, their paths, and basically their distances, etc. The shortest distance from the starting node. and you basically draw the same graph, same table again and again and again, where you're updating it in each step and showing what the update is. So the way I would want you to answer this question might be in terms of this graph as well. You can draw the graph again, or I think another way can be a labeled table, in a way that, whatever node has been labeled, whatever is the shortest distance, and whatever um, uh, is the path to from the starting point to that point yet is what is interesting to me. And maybe as a solution you can put up that. It's up to you. I personally prefer, the other point where you draw it as labels and as a table, as many tables actually. But if someone does it like this, exactly like it shows them in a graph and circles each and every visited label and correctly, counts this, I'm also fine with this, as this is a stepwise progression. And in this stepwise progression, even if you're doing it in a table or in a in terms of graphs, you must show a stepwise progression. It should not be a direct answer, right? Because in that case, I don't know if you have applied Dijkstra's algorithm or not, and I won't be able to assess you at all if you give me the correct path. However, if you give me each step, I'll be happy to give you full marks for it, even if there is some small counting mistake, etc., or something. It can be overlooked, but you need to come up with the complete solution and actually apply Dijkstra's algorithm. So each stepwise step should be given out. Okay, so let's call it the day for this particular section. In the next section, we'll be talking about section 10.7, which is about planar graphs, like how graphs can be represented in a plane and how we can cut them and stuff. So let's see you with more detail about planar graphs in the next section, section 10.7. Till then, I wish you all the best for this lecture, and I hope you've learned something. Take care. Allah Hafiz.